more of like a technical introduction to working internally in synthetic algebraic geometry. So what we normally do when we prove things. So you can have in mind that so the things I'm going to talk about are kind of the axioms that we use, and basically we will be able to look at Affine schemes. So because I'm talking internally, you could imagine that we're sort of secretly talking about some kind of big series of tuples, but this is not reflected in the language we use. So I would never say sheaf, basically I would say type instead. So officially, this means that we work in something like commodity type theory, but kind of informally. So if you're not familiar with commodity type theory, maybe you won't even recognize that I'm actually working in a commodity type theory here. So I will be using kind of network. I just want to make one important point about this. Which is that necessarily we are working constructively. So the law of excluded middle is this classical axiom that for any proposition, P either it is true or it is false, as well as the axiom choice. These are not available. In fact, they are false. So yeah, I don't want to get into detail about exactly what language we're working in, but okay, so let me start talking about algebraic geometry. So the starting point for all of this and for algebra in general is that we have some kind of base function. So you might think of this as a kind of axiom. It's a bit weird to call it an axiom maybe, but it says that we have some ring R. And this will be fixed throughout everything we do. And by ring, I always mean a commutative ring with one. Okay. So it's a bit strange to call it an axiom because it's really a data structure. Okay, we have some kind of base ring. And then algebraic geometry, in some sense, is the study of, loosely speaking, systems of polynomial equations. Okay, and what I have in mind here is that this ring R is kind of the base ring for all these questions about systems of equations. So I just want to give an example. You could consider the set of solutions with the system of just one equation, x squared plus y squared equals 1. So this is some kind of circle. Okay. And so these are kind of, this is some kind of geometric object. You know, you can try to draw a picture like this. So we have some kind of plane, and then this cuts out some subsequent return. Okay. Okay, and what do I mean by system of polynomial equations? In general, so in general, we have some number of variables, n, and we have some number of equations. where these equations are given by multivariate polynomials. I would call these variables T, just to distinguish them from the polynomials. So in general, this is some kind of geometric object. Let me call this X. Because it's something we can think of. I mean, we can imagine we can try to draw some kind of picture of what does the set of solutions look like. But it's given by algebraic data. It's given by polynomials. And kind of the key feature of algebraic geometry is that you have both algebraic objects around and also geometric objects, and there's some kind of duality that they somehow determine each other. So let me try to make this a bit more precise. So associated with this algebraic data, I can also define something, a kind of algebraic object corresponding to X. So take the ring of polynomials, and then you quotient it by the equations. Okay. So this is a ring together with a ring homomorphism R to A. So this is what we call it, it's an R algebra, and it happens to be finitely presented. So an R algebra, a ring is an R algebra if it comes with a ring homomorphism R to A, and it's finitely presented if it's of this form. So it's given by a quotient of a prolonged ring by a finitely generated vector. Okay, so this ring is some kind of an algebraic object, right? And so this kind of duality present in algebraic geometry is a kind of relationship between the ring A and the geometric object X. Okay, so we might think of X as some kind of a space, but and classically it would there's some kind of complicated space with a sheaf of rings. For us X is, we think of it as a space maybe, but it is literally a set or a type. So X to us is literally just this set of solutions with no a priori, no other term. Okay, so what is the relationship between A and X? So there's one kind of basic relationship which you can state without any axioms, which is the following. So for any R algebra, I can define the spectrum of A to be the set of homomorphisms of R algebras from A to R. So this is some kind of naive version of the Zariski spectrum from classical algebraic geometry, if you're familiar with this. But to us, this is a set. Okay, so it's a set of maps. Should I call it? Maybe I have it alpha 9, alpha from E to R, such that alpha respects addition, multiplication, 0, 1, and such that the composite is identity. Okay, so I can always consider this set. So this is some set that's not determined by the ring or the R algebra A. And so a partial answer to the question of what is the relationship between A and X is given by the following claim. So it's the claim that there is a bijection between spec A and X. So X is defined by A in this way. It's the spectrum of A. And why is this? So first we can consider the spectrum of the whole polynomial ring. So all R algebra maps from the polynomial ring to R. So this has a map to Rm, which sends a R algebra homomorphism alpha to the values of alpha at the generated polynomials C1 and T1. And this is a bijection. So this is kind of the universal property, if you like, of the polynomial ring. It's freely generated by these systems. So whenever if you want to specify a R algebra homomorphism from the polynomial ring to something else, you just have to specify where the generators go, then the homomorphism is determined uniquely. Okay. But my claim was about the spectrum of A and X. So X, by definition, is a subset of R2 It's the set of n tuples that satisfy some list of equations. Spectrum of A is also a subset of the spectrum of the polynomial. Okay, so this is because A is defined as a quotient. Because A is defined as a quotient, a map out of A is a map out of the polynomial ring that vanishes on the ideal. And if you think about it, vanishing on the ideal is under this bijection is the same as satisfying the equation instead of fine X. So under this bijection between spectrum of the polynomial ring and R2 the two subsets spec A and X are the same. So okay, any kind of set of solutions to some polynomial equations arises as the spectrum of some finitely represented origin. So this is that we can understand this geometric object X in terms of this algebraic gadget A. But it leaves open the other questions, or the question of going in the other direction. Can you recover A from X? And to this end, so we can say some things without axioms, and then we will kind of postulate an axiom that gives something much more precise. So what we can always say is we have a map from A. So this is a homomorphism of R. From A into the ring of functions from X to R. Okay. So you think of X as some kind of space. This is all the functions that you can define on the space with values in R. What is this map? It's kind of given tautologically. So if you have a ring element A of A, you have to define a function x to r. So let me use the fact that x is spec A. So I treat this kind of complexity. So I think of an element of x as, now I write alpha. I think of it as it's an element of spec A, so it's a ring homomorphism from A to R. And then I can just evaluate alpha at A. And it gives an element of R. Okay, so there is always such a map in any setting. It's kind of easy to define. And then you can think about the question, so to what extent does this kind of give a good approximation to A? So you can ask, is this map surjective? Is it projective? And so classically, the answer is always that in interesting cases, this map is kind of too naive to give a good approximation to A. So in a classical setting, you can always define functions x to r by a case analysis on whether your point is equal to a base point or not. You can define functions, that don't come from this algebraic gadget A. But all the kind of classical examples of functions that you can define here that don't come from here, they use classical axioms. So they use some kind of, if you have either axiom of choice or excluded middle, then you can define things in here that shouldn't come from here. But in a constructive setting, a priori, you cannot really say very much about this. And particularly, you cannot really construct very many elements of this that don't come from here. Okay, so what we do is we postulate the following axiom. So this is what Ingo Bleckschmidt introduced as synthetic quasi-coherent, but for now I would call it duality. So the axiom is that the map, this map A to R to X is bijective. So when I say it's bijective, in particular, it's an isomorphism of R, because it is an R as a problem. So I might also say it's an equivalence. So this, we call this the duality axiom because it gives, or maybe, sorry, this says inspect A, and this is for all represented R direction. So it gives a kind of duality between algebra and geometry. So it says that this algebraic gadget is defined by the corresponding geometric gadget. So this is kind of the starting point for our investigations. So there are a lot of kind of simple, I would say, more or less direct but interesting consequences of this axiom. Let me just give an example. So if I take A to be the one variable polynomial ring, then the spectrum of A is so I write equals. It's in bijection with R, and so we get following fact that functions R to R are in bijection with elements A, so with the polynomial. So it says somehow that every function R to R is polynomial. which, I mean, from a classical perspective, is very surprising. Basically, this classically, if R is a finite field, then it's true that every function is representable by some polynomial, but not uniquely. Here we have not only that every function is represented by a polynomial, but also uniquely. So this is kind of impossible in classical setting, because R can neither be finite nor infinite. Right. That's one example, and then yeah, it turns out that you can draw interesting conclusions from this, even using kind of very small parts of this fact. So a consequence of the duality axiom is that these two R integrals are in bijection. So in particular, I can ask, is this trivial? And I can ask, is this trivial? And the answer is the same in either case. So, but a ring is trivial if 0 equals 1. So I have that 0 equals 1 in A if and only if 0 equals 1 in R to the stochastic. Okay. And both of these things you can kind of understand more explicitly. So what does it mean that 0 equals 1 in A? So if A is given as this quotient of a polynomial ring, it means that what does equality mean in a quotient? It means that 1 is the ideal that a quotient by. So if this happens, there's also some kind of very concrete algebraic witness to this happening. On the other hand, what does it mean that 0 equals 1 in part of the spec A? This means that basically that if you have a point of spec A, then 0 equals 1 in R. So later we will introduce an assumption that says that R is non-trivial. So if R is trivial, then there's kind of nothing going on. If you try to do algebraic geometry over the trivial ring, everything is kind of vacuously true, and there's nothing interesting going on. So you want to assume that 0 is not equal to 1. And then this says that the spectrum, so then this says that if we assume R is non-trivial, this is that spectrum of H. So this is a kind of weak node-Schellensax, I guess you could call it, that if you have a system of polynomial equations, the only way it has no solution is if it's clearly inconsistent, if the equations generate one. Okay. So we'll give a couple of examples of this. So for if I just have one polynomial in one variable that's not constant, then, or let's say it's nothing. Then you can show that the ideal doesn't generate one, assuming so in this case, you can see already that the spectrum of for the quotient is not empty. So the set of x and r set of roots of f. So if you try to find a root of some monic polynomial of degree, which is a degree long, it's not true that there is no root. Okay. So this is a point where you can kind of if you like kind of classical X, to just remove the not and say that, okay, if it's not empty, it means there exists a point. And this is not something you can do. So this kind of almost says that R is algebraically closed, right? So saying R is algebraically closed would mean that there exists a root. Here we're saying there is not no root. There not is a root. So it's a kind of a weak version of algebraic closure, which turns out to be the it turns out that actual algebraic closure is just not validated, but we have this version. Okay, another example I wanted to give is so if you consider a ring element R of R, and then there's two finite represented R algebras to consider. There's the algebra where you force R to be 0 and the one where you force R to be invertible. Okay, so what do each of these algebras tell us? So in this one, spectrum is the proposition that R is 0. So this is a kind of trivial system of equations where there is no unknown, and the question is just, is the equation R equals 0 true or not? So the spectrum is it's a proposition in the sense of multiple types of it. So we think of it as a type. And what this tells us is that it's not the case that R equals 0 if and only if R generates the unit ideal. So this is I'd write this as saying R is invertible. Okay, so again, this is assuming 0 is not 1 R. So the invertible elements are precisely the non-zero elements. And the strong direction here is the one that goes from saying R is not 0 to the one that says that R is invertible. And this is, so you might think this is surprising if you're kind of, usually when you write constructively, a negated statement is kind of weak and something that you cannot really extract positive information from. But the statement that R is invertible is actually kind of very positive. It says that you have yeah, I mean, if there's an inverse, then it's unique. So saying R is invertible, it means that you can actually recover the inverse for R. So you're going to do something negative, do something positive, which kind of seems surprising. And then this other example, the spectrum of this localization. So this is the prolonged ring in one variable quotient by the equation that this variable is inverse to R.
Could you use a new blackboard because it gets very small?
Yeah. So I wanted to consider this ring. The spectrum of this is the proposition that R is invertible. Okay. So in order to define an R map from R localized at R to R, it has to be the case that R is invertible enough. So what this duality tells us is that it's not the case that R is invertible if and only if 0 to 1 in the localization. And it turns out that this there's a characterization of when do things vanish in a localization, and this says that in particular one vanishes if and only if there exists a natural number n such that I already then vanishes. So the non-invertible elements are the nilpotents. Okay. I think that those are the examples I wanted to give of consequences of duality. Right. Now I want to make some definitions. Okay, so we want to think of these affine schemes as somehow spaces. So in particular, there's like a good notion of open subset of an affine scheme. So let me write now F for an element of A. So any element F of A determines a subset of spectrum of A, which is set of points X of spec A where so now we get this funny notation X of spec F. This is the evaluation of a point of spec A at a point at a ring element of A. So it's usually more convenient to write this Fx. So the set of points where Fx is non-zero, which equivalently means that it's invertible. So this we think about as an open subset, and then associated to this with also a closed subset. To be somehow, we think of spec A as some kind of space. There's some kind of zero locus of F, where F equals 0 here. So this is the vanishing locus of F, and then its complement. Everything else is DF. D stands for vanish. Okay, so this gives some kind of approximation to a topology on spec A. We can talk about at least these kind of basic examples of closed and open subsets. And related to this, I wanted to find also if you have a list of ring elements of A, you can talk about G also for the list of them, which is the okay. So there's kind of an expectation If here we use classical algebraic geometry, which is that whenever I have a list of elements like this, I can ask, is this all of spec A? And this should happen differently if the elements generate the that will be. So whenever we have a kind of partition of unity in A, it should induce a kind of open cover of the spectrum. And in order to make this true, we introduce an axiom. So this is the second axiom, I guess, if we don't count the assumption that we had on the ring. But sometimes I think this is presented as the first axiom. So the ordering is kind of inconsistent, but so the thing here is that R is a local ring, and so there's a meaning of what does it mean to be local in a classical setting, which is kind of talks about maximal ideals. For us, this means something much more concrete, which I spell out. It means that 0 is not 1, and roll or in our either or is invertible or 1 minus r is. So this is kind of one way of saying what does it mean to be local. Another way of saying it is that if I have some sum of elements, this is invertible. If this is invertible, then one of the summands is invertible. So to be clear, this is a disjunction of propositions. And in particular, so whenever for any element R, you know that kind of at least one of these is true, but you cannot kind of coherently ask which one is true. But you know at least one of them is true. Great. So maybe I should given this axiom, we can now prove that this is can we okay, so we can prove using this axiom that if you have some ring elements that generate the unit ideals, then the corresponding open subset of A, we call it. And the proof is let's see, so so given a point, X is speculative. You can evaluate on these elements of A at X. And because already in A they generate the unit ideal, so these are elements of R. in particular, when you evaluate the x, they still generate the unit ideal of R. Okay. So it means that you have some kind of combination, like sum of the Ri x equals 1. So you can, from this, you can deduce that from the assumption that R is local, that there is some index I where Rif is anywhere. And then this implies that fx is already inverted. Okay. So let's see. So yeah, so this assumption of locality means that we have some kind of open covers of the affine schemes. So I don't know if I ever said, did I say that the type of the form spec A with the finite percentage R is affine scheme. So I mean, this terminology kind of makes sense mostly if you know also about more general schemes, which we'll see in the lecture after lunch. Okay, so the assumption of locality. I wanted to give one example of this. So so that A again be the one variable polynomial. Consider the two polynomials f1 is t and f2 is 1 minus t. Then we have the df1 union df2 is all of spec A, which remember is R the set, and when we think of R as not as algebraic object as a ring, so here R is like a set. We prefer to denote this by A1. So then this claim said that if you look at the line, you have kind of so this is a picture of A1. There's the point 0 and the point 1, and yeah, df1 is somehow everything except for 0. Df2 is somehow everything except for 1, and then we know that when you union them, you get all of them. Actually, this is kind of a direct retracement of locality. So any point at A1 lies in at least one of these two. Usually in both. Okay, so another way of expressing this is that so whenever we have some elements, ring elements of A that generate the unit idea. So we know that we can form dfi for each I. And let me now, instead of taking a union, take a disjoint union. So I write this kind of square sharp with the sharp edges to denote it's a disjoint union. Or a co-product if you like. This obviously comes with a map to spec A, which is just on each component the subset inclusion. And so what we said is basically that this map is surjective. Okay, so I draw this double arrow to the map is surjective. Yeah. So related to this, there's a kind of choice principle, which will be the last axiom of our development. So this is kind of forcing surjectivity of some map where there is no clear inverse. And in general, you can show that there is no inverse. Like in this example, you cannot find there is no map that goes from R to CF1 discontinuous. CF2. That's no, there's no section. So this is somehow related to some kind of choice principle. So classically, the axiom of choice says that any surjection has a section. We shouldn't expect the axiom of choice to hold in our setting because we're working constructively. And this is kind of actually an example of the failure of axiom of choice. In fact, if you know about kind of pre-sheaf categories, there's a true fact that any representable object of a pre-sheaf category is projective. So, and spec A here is something like a representable object. So, in a pre-sheaf category, you would expect that spec A is surjected, so that you will always find these sections. But what we're doing here is we're kind of forcing the existence of some kind of surjection. So we no longer have that this is projected, we don't have choice over it, but we have some kind of weaker version of this, which I say now. So this is the axiom of the local choice. So it is that for A or the ground. And we need some arbitrary type with a surjection. This surjection is somehow explained by a surjection of this form. So the statement is that there exists some natural number with a list f1 up to fn ring elements of A, and then I can make this. Sorry. So this actually doesn't give you. Oh, yeah, sorry, I keep. It's okay. It doesn't give you a section of this surjection field. This would be too much, but it gives you a surjection after passing to some open cover of the spectrum. So this is the most recent axiom introduced in this development, and it's kind of opens up the possibility of proving a lot more things in front of you. Yeah, but it also probably the most kind of scary looking axiom, and it's kind of strange in how it quantifies a lot over some arbitrary surjection and some arbitrary open cover. Oh yeah, and I want to emphasize, I guess I've already done this a bit, but there is a kind of a tension between these two axioms. So the assumption that R is local, it's a nice axiom in that it tells us, I mean, we can do things with R that we wouldn't otherwise be able to do. And there's a tension in that, the more things we assume here, the weaker our choice axiom is. So you could think of like variations of this whole development where maybe you put more assumptions on R, then it's not just local, maybe you have some kind of something like algebraic closure or something like this. And then if you want to do that, you have to weaken this even further to allow even more probability. Yeah. Okay, so I just want to, for the last section of the talk, I just want to kind of state, I guess, one particular corollary of this, or a consequence of all these actions together. So first I make a definition. So an open proposition is a proposition of the form. So a proposition that illustrates that, for some list of ring elements of R, at least one of them is invertible. This is what we call an open proposition. So it's a kind of you might think of it as an open subset of the point. So, and again, classically, this is kind of strange because classically, if you have excluded middle, then so by one in the middle. I mean, classically, any proposition is either true or false, so it kind of doesn't make sense to, ask more things about a proposition. In this setting, so okay, for example, the true proposition.
Maybe one just shouldn't call it a point.
But it is,
yeah.
From the internal perspective, it is a point. To give an example, the true proposition top is open because it says that one is invertible. One is invertible indeed. The false proposition is also open. It's the empty disjunction, if you like, or the proposition that yeah, and then so the result that I just want to state is the following item, which, if I remember correctly, is 4.27 in the paper on a foundation for synthetic algebraic geometry, which is the following. So again, for a finite presented algebra, there is a bijection between so on the one hand, the set of okay, I should first expand on this definition. So an arbitrary subset is called open if for all x in x position that x is in U is open. And maybe I should stress here that to be open is a property. So we're not, it means that for all x in x, there merely exists some representation that makes x in U equivalent to this. But let me not say too much about this. Okay, so given any kind of class of propositions, there's a corresponding kind of class of subsets, just defined point to it like this. That's an instance of this is an instance of that construction. So this theorem says it describes all the open subsets of affine schemes. Okay, so you can form the collection of all open subsets of spec A, and then you can ask what is this? And then what you get is the following. So it's a set of radicals of fundamental ideals. Okay. So what does an element over here look like? It's given by some list of elements of A, and then you form kind of their ideal, and you take radical, and this radical only ensures that there's some kind of you forget some aspects of this ideal in some sense. And you can describe explicitly this map. It's the map that is the scheme. Yeah, so Felix kind of mentioned this result before. It's somehow clearly desirable, but also quite surprising that you can prove it just from these axioms. So just to give an indication of, I mean, what you have to do here is, you're supposed to start from some arbitrary open, and you have to produce this kind of very explicit algebraic data that witnesses this being open. And this involves a lot of kind of this choice principle and some other things, and eventually it kind of reduces to some principles of like Zariski descent, I guess you could say, for this set. But yeah, I just wanted to mention this term, and I guess that's all I have time for. If we have time for a couple of questions.
Yeah. The lunch break is very generous to us. Yeah, okay. Maybe. So, like, I want to ask you as kind of a technical aspect of, because you mentioned like we're working hard, so all the bijections you mentioned are equivalences, or?
Yeah, but so right, maybe I didn't say this, but everything in this talk and for most of what we do is working with zero types or H sets or sets.
Ah, okay.
So indeed, they are. Yeah, I mean, the concept of an equivalence of types is just it reduces to the notion of a bijection or isomorphism or isomorphisms.
You mentioned two forms of openness and closeness. Can you relate these to each other?
Yeah, so an open subset, an open thing is the complement of a closed thing.
Okay.
And then it turns out that you cannot actually go the other way, because when you look at opens, you kind of forget to. They're related to how we take radicals here, but I think this. Yeah, but every open is a complement of a closed, and not vice versa.
Yeah, so maybe two comments. I mean, one about pictures. I mean, for those who are not that much used to algebraic geometry, I mean, I mean, often it makes sense just to, to depict an open subset by just drawing the complement, which is closed, because this is more like open subsets look in Zariski topology. So if one draws them like one does in calculus, I mean, the picture one gets in one's mind is just wrong in general. So, yeah, and also sometimes it also makes it easier. I mean, and then of course one has to, union is then the section of the things one draws that are not in the set. Yeah. So here it would just be marking 0 and marking 1.
Right,
picture.
yeah.
So one set does not contain 0 and the other set does not contain 1, and it's clear that because the intersection of 0 and 1 is still empty, the union is empty.
But in this justification, you kind of implicitly use locality, I guess.
Yeah.
Yeah.
So it's, and then you mentioned, you said, well, at the very beginning, that spectrum of A is naively classically just the algebra homomorphisms.
Yeah.
But I mean, a bit more precise would be, well, these are the R value points
Right.
of the spectrum of A. And then, I mean, for those who know these things, I mean, then they may see the link to the rest.
Yeah.
And to the top also. Yeah, not just.
And maybe another question is, so like you define this notion of open be kind of an absolute one, but it depends on the local ring you choose. So if you start with another local ring, does the open stays the same or it changes?
I mean, so usually we think of R as fixed for everything we do, so we never consider a different. I mean, you could like move. So considering another open ring is something you could do if you move to a completely different topos, but then they're not available.
Yeah.
In the same universe. So for us, we just have one R, but everything is like parameterized over.
Well, but you can of course add further axioms restricting what rings you can have externally representing R, and depending on the extra axioms, you may have lots of opens or just few opens.
Yeah. I mean, in general, one kind of surprising thing about this whole development is that internally, most things are kind of insensitive to what base ring you started with to construct your big Zariski topos. So I don't know, maybe yes, but internally, I mean, for example, there's this kind of surprising thing that the internal ring R is always kind of almost algebraically closed in this sense, and never like truly algebraically closed. Both of these are completely independent of what ring you started with. Doesn't have. It could be algebraically closed, or it could be something different.
Yeah, but I mean, for example, we can just add the axiom that 2 is invertible.
Right. Yeah. This is something.
And then you lose some interesting opens or closes.
Yeah, that's really yeah.
Okay.
So or maybe if you don't know how much you know about classical algebra, so if you say you have those the field Q and get the spectrum of Q, then when you do algebraic geometry over this field, then it's just a point.
Yeah.
But when you take a look at the état topology of the spectrum of Q, then you see all finite algebraic field extensions of Q.
Right.
So it has lots of état opens, although through some other lens, Q just looks like a point, but it's not. And now if you replace Q by say some algebraically closed field, then all these opens vanish. You do not have them anymore. So it's the same here.
Yeah, thanks for the explanation. Maybe like, okay, the confusion I had is that because you presented these axioms, in my mind, okay, we're working in kind of the classifying topos of search and local rings. Is that the correct picture to have in mind? Because this is very different from, say, what you just said, because you have a fixed external ring of Q or ZP or whatever, and you work in the topos of that, say the topos of that.
Yeah, so I think we will hear more about kind of the intended semantics of all this tomorrow, but the idea is that, so we're working in the big Zariski topos, which I guess is the classifying topos for a local K algebras. Right?
Yeah.
So you have some base ring K, and then you.
Yeah, but you can change K.
Yeah.
Yeah.
Okay.
somewhere basic question when you said, what is our algebra homomorphism?
Yep.
Why do you need this condition? I mean, you say, oh, it should respect the operations plus times 0, 1, but what is the other condition? I mean, it's about the identity. Usually you don't have this in a morphism.
Yeah, so if I don't have this, then it's a morphism of rings. But A and R are both are algebras. So yeah, this is saying that we respect the R algebra structure. So for example, it means that you can kind of one way to write it is that if you have some element R and some elements of A, you can multiply A by R. This is kind of what it means to be an R algebra. And then this condition says that this number alpha is linear in this way. So you can break the R outside, or equivalently alpha R is R, which is what I wrote it. It's a kind of R linearity, but it's because we're working not just with rings, but ring extensions of R or R. So you have to respect this structure. And if you don't respect this, then you get kind of way too many homomorphisms. I think, which I don't know exactly what. I want to say I get to win, but I'm not exactly sure. Okay. There's no.
Very good. So thank you. So now we will do the lunch break. So the room stays open, so you probably should not leave your stuff here.
Yes, I think so. I guess we'll just make this sort of.
Yes.
I know we can't know how to keep it close.
You don't have a key close. No, but you can leave your thing in or at least. Well, get out of them.
I don't know if it's really costly. Well,
How are you? Oh, yeah.